today. You're going to see probably more slides than usual, so there's a lot that we're going to go through, so you might get hit kind of heavy with the lecture today on this, but remember, we're still rolling it up onto the web. How many of you have accessed the web? All right, does it work?
Yeah.
How about the lectures? A little weak?
You can't even, won't upload.
It won't upload?
No.
It should. They're in compressed. They're in MPEG. All right. So as the MPEG, then it's compressed. But I have no problem playing it on my system. If you download it or you drag and drop, maybe that's the reason. But anybody else having trouble with the videos?
Has anybody else tried the files?
If I try them, yes. Okay. Well, let me know if there's some problem. All right, we're going to start into linear algebraic equations. That basically means you're going to be solving simultaneous equations. You're going to be using matrix methods to do this. You can do them either as iterative techniques, or you can do them as direct solutions, and that's generally what we refer to as Gauss elimination or variations on Gauss elimination. Lots of techniques and numerical schemes to solve large matrices. There's still a lot of work continuing even today to come up with ways to solve large matrices. Principally in solving like CFD models or structures problems or things in which you have a lot of very, very large matrix type equations that you have to solve, and you want to come up with fast routines to do that. Some of the newer schemes now being examined include what are called Krylov techniques, advanced frontal methods, skyline schemes, and LU decomposition. That means lower upper decomposition. So these are techniques and tricks that we've tried to employ and utilize to solve matrices in a very fast and efficient manner. You will find that will become a very particularly intriguing problem for you when you're doing things like finite elements in structures or heat transfer or what have you, where you're coming up with very large matrices and you don't want to have to wait 3 or 4 days to get a solution from the computer, even if you're running on the supercomputer. So the matrices are very, very important. All right, let's go back to this bungee jumper for a minute. This time, you and 2 of your buddies have decided to jump on this cord. So I don't think I would want to risk that, but anyway, let's assume there are 3 of you. This is the positions that you would be in at 0. And ultimately, when you jump, then you get a stretched line as you see here. So what you want to do is to formulate the governing equations for this. All right, so what you're going to do is establish free body diagram. All right, so here's the first free body diagram. The forces that are pulling on this, right, are on the person. Of course, the tension that you're getting from the cord and then the weight of the other jumpers. Here's the fellow in the middle, and here's the fellow at the end. So here are your 3 equations that you have for each of these jumpers, okay? So you got 3 equations to obtain the masses for the 3 jumpers. So what you want to do now is combine all those together. So you have, in essence, these 3 equations that you have to solve simultaneously. All right, so you can't do it as a linearity, that is solve one and then go to the next one and then go to the next one after that. This is what those equations would look like, right, if you wrote them out for each of the bungee jumpers. I can rewrite this in terms of that matrix. All right? So here is the 3 by 3, so those are the masses, and these are the unknowns that we'd be solving for. So, and then the right-hand side, all right, you see the influence of the body force, that's gravity pulling down on these jumpers. Okay, so we can rewrite that in a more succinct form as a 3 by 3 matrix. We will come back to that later when we solve the matrices. Here's another example dealing with chemical reactors. Right, you've got a feed line that's coming in, some processor here. It gets bifurcated and goes off into these 2 paths where you might have some other reactors or whatever that are in the system. Basically what you're doing is a mass balance, and you're saying, gee, what flows into this thing ultimately has to balance what comes out, but there's a lot that goes on in between. I mean, maybe I want to know what the process is in here or in one of these other reactors. It's almost analogous to an electrical circuit. Idea. This is what might happen if you have a series of chemical reactors. All right, so now you've got a feed stream coming in here, you've got one coming in here, which is also participating into this feed stream. So ultimately what you're looking at, gee, these things could get kind of complicated. And there's just no way that you're going to be able to sit down and handle this when you're trying to do it by hand. So this is where you can really capitalize on the strength and power of the computer. Okay, the Q's generally denote a flow rate. There's some mass that's moving through. All right, what it means is simply this, that we're dealing with a matrix. And so we call the internal values within the matrix elements. Right? So if that happens to be A, the matrix A, then it consists of all these elements denoted by the lowercase a. All right? And so we label these things according to their position with regards to row and column. So A11, row 1, column 1. 1, 2, row 1, column 2, and so forth. Right? Until we get down to as big as the matrix is that we want. Okay? Here would be, obviously, row 2. So second row, third column. Right? So everybody get the idea?
Yes.
Okay. All right. Now this is an important rule. You must remember this. You can multiply matrices only if the inner dimension is the same as the other matrix that you're multiplying by. All right. So that means if I have something that's m by n, multiplying another matrix that's n by l, the two n's must match, the two inner dimensions. All right? Ultimately, what I wind up with then is an m by l matrix. All right? Get that idea? Now, we'll do an example here in just a moment. But that's the rule of thumb. All right, let's do a quick review. What do we mean by matrices? A row matrix. A1, A2, A3, A4, and so forth. It means it's written as a row vector, all right? Kind of like thinking of it as a horizontal matrix, all right? If I have a column vector, I would write that like so, all right? So notice up here, I have one row, a bunch of columns. Here I have a bunch of rows, one column, all right? That's the difference, all right? Row matrix, column matrix. If I have a square matrix, square, implying that I have the same number of rows as the same number of columns. Right? So here I would have a 3 by 3. Right? A symmetric matrix. What do we mean by symmetric? Take a look at this. What do you see that's common about that matrix? The off-diagonal terms, right, are the same about the main diagonal. The off-diagonals. Right? That's called a symmetric matrix. We would capitalize on this later where we say, gee, I only have to deal with the lower part of this or the upper part of this because it's symmetric. I would be doing the operation twice. I don't have to do that. A diagonal matrix, obviously just what it implies. You have a diagonal consisting of, say, these elements that are running down the diagonal, the main diagonal of the matrix.
So would those all be like 1, 2, 3?
So A11, A22, A33, right?
Are all the rest zeros?
You can, generally you can have zeros sitting in there, all right? In this case, if I had a diagonal matrix like this, that would just be a one diagonal. The rest of these would all be zero. In fact, you see it down here on the identity matrix? That doesn't mean that you have zeros sitting in here. You may or may not, right? But generally on the identity matrix, when you have one setting on there, it's implied that these are zeros. All right, so you'll see a little later on in dealing with lower and upper matrices here that sometimes you'll have this setting on the main diagonal, but you'll have some numbers in here, but up here it would be zero. In this case, in the identity matrix, you're saying these are all zero, these are all zero. That is all the off-diagonal terms, right? And the value is 1. Now, what it may have out here is maybe a value that's divided by some number so that it makes that unit or that diagonal a value of 1. Okay? We'll see this later when we actually do an inverse matrix. Okay? Now, this is what we mean by upper triangular, right? So all of these down here would be 0. Here's the lower triangular, right? So all of these again would be 0. Setting up there. Banded matrix. All right, so here you see, oh, I've got a main diagonal here, I've got an off diagonal here, an upper and lower. Okay, what's the bandwidth of that matrix?
4.
What do you mean by bandwidth?
That's what I want you to figure out.
4 by 4, isn't it?
I'll give you a hint, it's not 4 by 4.
2 by 2.
No.
I don't know what you mean by that.
Okay, look, I have how many diagonals? 3. That's known as a tri-diagonal matrix. All right? The bandwidth would be what?
3.
Would it? Or is it 2? Main diagonal, 1 on this side, 1 on that side.
Oh, okay.
So what's the answer?
2.
What do you think? I
I'll
want
say
you to
2.
think about this. I want you to go probing and say, what does that mean? What's that really mean? All right? Okay, matrix operations. Notice I can add Aij plus Bij. Matrices must be equal. What? N by M. All right? Subtraction, same rule. Okay. No, addition and subtraction. Commutative and associative. What do I mean by that? Remember that in mathematics? Go ahead, tell them.
Well, the first matrix multiplied by the second matrix is the same as the second matrix.
Right, you can flip them. Doesn't matter what order. All right?
So-
Multiplication.
What is the bandwidth? Is it 3? Is it 2? Is it?
He wants you to look at it.
I want you to find out.
Okay.
Multiplication. I have an Aik times a Bkj. All right? What do we know? What works here? An N by M can be multiplied by a M by L. Right? Why does this one work? Because the two, right? Those two values are the same. All right. Assume that we want to multiply two matrices, A times B. A is a what?
3 by 2.
A 3 by 2. 3 rows, 2 columns. And B is a 2 by 2. All right. Now what are we going to do? We're going to take that matrix times that matrix. Will it work?
Yes. The inner terms are the same.
Right. You can do that. All right. What you will get will be a 3 by 2. Right? Now let's see what happens. So you're going to take 3 times 5 right here, and 1 times 7 added together makes 22. That's the first value setting in here. You're going to do that same process for the second column here for each of those terms. So you're going to wind up with a 3 by 2. Right? That's what it looks like. Let me stress, be sure you can do this. If you haven't done it before, or you say, gee, I did that 100 years ago or whatever, go back and refresh your memory. Be sure that you can do this. Right? And that you get the elements correct. That is, that they go into the right spot in the resulting matrix. Okay, in fact, I put a little note there. You notice, as a homework assignment on your own, verify that you get those values in that 3 by 2. All right? You must do the proper multiplication, row and column. All right. It is possible to multiply two matrices if the number of columns of the first matrix do not equal the number of rows of the second matrix. Or, sorry, it's not possible. It is impossible. Okay. Is the multiplication of matrices commutative?
No.
Okay, who said no? Okay, why is that?
Well, if you switch the order, you're multiplying interior dimensions might not necessarily be the same.
Exactly. Because of the order that you're doing this operation, if that switch, what's going to happen? Oops, you got big trouble, right? That is, you're going to get a different result. All right, matrix division, not a defined operation, as in multiplication. This starts to get a little tricky. Assume you have a square matrix A, and it's non-singular. What do we mean by non-singular?
Has multiple dimensions.
The determinant is not 0. Okay? You'll find out. We want to find the inverse of the matrix A. That's denoted by that little -1. That's what it means. When you see that, it means inverse in a matrix. All right? Notice that we've identified matrices in terms of braces and brackets. Right? So when you see a bracket like this, it generally means it could be a matrix with multiple elements, rows and columns. All right? When you see something that actually looks like this, what do you think that means? It means I have a column, right? I have a column. All right, it's only either one row or one column, whatever it is. Those are the braces versus brackets. Sometimes books will use that, and it's just implied that you know what that means. All right, so look, if I take a matrix and I multiply by its inverse, right, what am I going to wind up with? What's the I? The identity matrix, right? It means I get a column, all right, I get a diagonal of 1, all right? So it's analogous to division. So you get this identity matrix I. Now, let's see what happens. If I have a very simple 2 by 2 matrix, that's the smallest unit matrix operation I can do. All right, so I have a 2 by 2. The inverse actually looks like this. And so you go, hey, what's happened here? These things aren't what I saw before. That's because there are certain things that you must do to get this in this proper form. That's what we're going to talk about. Okay? A couple of more definitions with regards to matrices. All right, when you're dealing with a 3 by 3, or certainly larger matrices than 3 by 3s, then you have to do what's called dealing with the transpose and the adjoint. All right, what do we mean by the transpose of a matrix? Take a look right here. Here's the main diagonal. Does this make sense? What did we do?
You convert the rows into columns.
Yeah, the off-diagonal terms flip. You are transposing from a row to a column. Right? Does everybody understand that? Underline that word. That becomes important. So I'm switching from a column to a row. Yeah.
I'm lost. Can you do one on the board or something?
Look right here. The main diagonal, the 3 by 3 that I would originally have would be A11, A12, A13, right?
Right.
First row, second column, third column. What I did was to flip-flop these, see? So here, that should be an A21, A22, A23, right? So I transposed these values from the main diagonal. Get the idea? Okay. All right, so look, Aij, if I denotes the row and J denotes the column, and I have a little T up there which means transpose, what's that equal to? Aj. Right, understand? This is a subtle way for us to eventually get you into Einstein notation. So if you ever want to get into understanding what Einstein wrote in mathematics and dealing with that and turbulent flow and all that stuff, it means, I think in terms of these little subscripts. So I know what they mean when I see them. All right, so here's that brace I was telling you about, right? So here, let's assume I have a column vector, A1, A2, A3. right? If I want to take the transpose of that, what would it be? What would this be called? A row vector, right? So the transpose of a column is equal to a row. The transpose of a row is equal to a column, right? Okay? All right. What do we mean by the adjoint of a matrix? Adjoint. You're going to see a little abbreviation there that says ADJ for adjoint. It means it's equal to the matrix cofactor transpose. Where'd that come from, right? So here's the cofactor, the transpose of the cofactor. Now I'm going to show you what that is. All right? Cofactors are obtained by replacing each element times the quantity minus 1 to the I plus j, right? Times the determinant of a reduced matrix, in which the I and j rows of the array are removed. Now you're going to see this. Once you see it, it's going to be obvious. And in fact, you did this in junior high and high school. They may not have called them cofactors and so forth, but that's what you were doing. All right. What I want you to do, find the cofactor adjoint inverse of this matrix. Let's take it very simple. Here's a 2 by 2, right? So you see A11, A12, A21, A22, right? Okay. Now, take a look at what happened when we created the cofactors. What did we do? Take a quick look. Anybody see the pattern? Okay, so we had the little rule of thumb on the last page, but if you look at this, you'll go, oh, now I know what it is. It's simple. All right. Notice that I switched these, right? What did I do here? I switched these and even, odd, even, odd, even. See the size of the matrix? All right? So see what happened? That's where that minus 1 comes into play.
So you flipped it from about both diagonals, you flipped it this way.
So it's a transpose and a change of sign on the off diagonals. Okay?
Well, but it's not a transpose,
It's not
because
just a
A
transpose, it's
one
like-
is in the upper left.
See right there?
But a transpose would have A11 in the upper left, right?
Well, here, what I did was, see, here's A11, so I switched these two. Here's A12. I put A12 down here, right? Then I had that minus 1, remember I plus j? So this goes 1, 2, 3, 4, get the idea? Right? All right, so then I just flipped these, right, up here, and then added that minus sign. So that's the only difference, that's what you're doing. Now, let's look down here. Here's the adjoint, right? Now, what did I do in the adjoint? It's almost a triviality in a 2 by 2, right? So in the adjoint, what I did was, oh, now I got to take the transpose of that thing, of the cofactors. Remember, CF to the T? So it's the transpose. So that means, oh, now I'm going to take these things and I'm going to put them back again, right? Only I'm going to retain the sign.
For every other one.
The point here is that it looks very, very trivial, but think of what's going to happen if you're dealing with a 3 by 3, a 4 by 4, N by M, or whatever it would be. It'd be huge, right? That's why you set up these rules in the computer so that it knows to do this. All right, so if I want the inverse of this matrix, then it's the adjoint divided by the determinant. Right? Now, is there anybody who has trouble finding the determinant of a matrix? Right? I think everybody's been through that probably 100 times or better. Right? So very simple. Here's the determinant. Right? You can't have 0. Right? Otherwise, what? Wouldn't work. Right? So here's the adjoint sitting up here. So the inverse of that is going to be whatever these values are going to be divided by the determinant.
We're going to have to do the determinant, are we going to have to do the determinant for 3 by 3 matrix?
Sure.
I mean, by,
Why, you want the computer?
Yeah.
Well, you can if you want. I guess. We can plug you in and make you a computer. In fact, I'll give you a 10 by 10, but that'll keep you busy for. Okay. What do we mean by finding the minors? So now let's go to a 3 by 3. Remember, the smallest you can reduce a matrix is ultimately to a 2 by 2. But anything larger than a 2 by 2, 3 by 3, 4 by 4, whatever, consists of a whole bunch of 2 by 2 matrices. So in the end, if you get it down to a 2 by 2, you go, oh, I can work that by hand, right? But anything bigger than that, boy, it's just repetitious. Let's let the computer do it. Now, what do we mean by finding minors of a matrix? Here's the matrix. Here's a 3 by 3. All right, so what I'm going to do is find the minors. So if you remember from many years ago, take this first value, and then you're going to be dealing with a 2 by 2. And you're finding, in essence, the determinant of that 2 by 2. And that's what this is, right? So that value times the determinant of that 2 by 2. Now I'm going to go to the next value. But remember, every time I go to the next column, I change sign, right? So now it's a minus. So I've got the minus up here. Then I eliminate that column, eliminate that row, and I have these two values and those two values. And I take the determinant there, right? Then I go to this value, I find it over here, and so forth. Remember, the L's means dot, dot, dot. Okay? So ultimately, when I get down to this one, right, here I am at the end. Here's this value. Where's the 2 by 2? It's going to be those 4 values right there. All right? That's what we mean by taking and finding the minors of a matrix. As you can see, what's going to happen if I go to a 4 by 4? How much work is going to be involved? A bunch. How many 3 by 3s in a 4 by 4? And then how many 2 by 2s in a 3 by 3, and so forth. You see what happens? Every time you add a row and a column to a matrix, it really significantly multiplies the amount of work that you have to do. Okay, transpose the off-diagonal terms. Remember these, what we just found before? If I transpose them, right, just like we did in the 2 by 2, I will get the cofactors, right? Okay, so I can do that. Once you've found the cofactors, you can find the adjoint by performing the transpose of the cofactor terms. Okay, so you just transpose again in this thing. So now you've found the adjoint of this. Okay? The last thing you want to do, you would then find what? You would find the determinant of the 3 by 3, you would divide that into the adjoint, and you would have your inverse. Now let's see what happens. Find the inverse of A. Here's a simple 2 by 2. Here are the cofactors, right? What did I do here? Flip-flop these, change these, do the sign. Find the adjoint, right? Just flip-flop these back. I take the transpose. All right. Now what I'm going to do is find the inverse here, so that's the adjoint divided by the determinant. That should be times, not G. All right, so here is my adjoint. Here is my determinant, which turns out to be 2. There's my inverse. All right. Does anybody, I strongly suggest that you do this as an exercise yourself, just to be sure that you can get the inverse of that simple 2 by 2.
So to do a 3 by 3, you have to break it down into the 2 by 2s?
See, ultimately what you want to do is to set up your algorithm so that the computer can do that very quickly and efficiently. And that means having it go into ultimately the 2 by 2s. Right? So you can work it out by hand. So that's what you got to do. Well, what you want to have the computer do it. Right? Let it set it up to do that. All right, now some other matrices just to make you aware of it. The trace of a matrix, all right, that's the sum of the principal diagonal elements. Why do I know that this is the principal diagonal? See that index right there? What does it show? I, right? So it means I'm down the main diagonal of the matrix.
You just add them up.
Yeah, so, and basically that's the summation, I'm just adding them up. That's the trace. An augmented matrix, obtained by adding a column or columns to the original matrix. So let's assume that I've got this original 3 by 3 matrix. I've got a column matrix over here, right? Or a column vector. We refer to them really as vectors. So what I want to do is just add that to this. So here is my augmented matrix, right? I've basically added just another column. All right, why do we do this? As we say, augmenting a matrix, it's usually when you're solving linear systems of equations, all right? And ultimately, I will show you later that you can manipulate an augmented matrix to actually find the inverse, instead of going through the procedure that I showed you. If you were, obviously, if you were trying to do that by hand, it would be pretty difficult if you had a large matrix, right? But actually, that's what a computer is doing. It's going through all those steps for you. This way, if you're doing an augmentation, sometimes it's very easy for something like a 3 by 3 or even a 4 by 4 to work out what the inverse would be. All right, now, next week, we're going to talk about Gauss elimination. You did Gauss elimination yourself when you solved 3 equations simultaneously by hand. All right, so you had x1, x2, and x3. Find x1, x2, and x3. What is it? All right, so what you want to do is to review the notes, look at chapter 9 on Gauss elimination. That's the most fundamental direct solver for dealing with matrices. Everything kind of spins off of Gauss elimination. From Gauss elimination, we will go into something called a lower and upper decomposition. And what we're trying to do is to simplify the amount of work that either you or the computer would be doing in solving a matrix. Sometimes there's just no way we can get around it, and it just has to be done more or less as a brute force. But in most situations, we can capitalize on some tricks of the trade in dealing with matrices. Okay, now, let me also mention one thing here. In most engineering problems, you are always doing something that looks like this. Everybody see that?
Yes.
You're taking the matrix, or a set of equations that you can write in matrix form as A. The unknowns are X, and everything is equal to whatever is known on the right-hand side, AX equal to B. All right? That's what we're doing. Almost every problem that you deal with in engineering or science is going to be of that form. Okay? Any other questions? All right, and I'll see you on Tuesday.